Hi, so let's start with the new topic that is SPI. I hope UART and I2C, which I explained in earlier videos, are clear. So today we will be looking into SPI from the interview perspective. What questions are asked and what is the important points that you need to keep in mind from the interview perspective. So let's start. So first thing, SPI is a serial peripheral interface. So peripheral means it works on the pins at the end of the microcontrollers, and it's serial interface. Okay. Now the first thing to be kept into mind that in an SPI only one master is possible. In any SPI communication, the master is one, slave can be many. So in theory, there can be infinite number of slaves, but the slaves are limited because the any master cannot have infinite number of chip select pin. So let's look into what all major component in SPI. First thing, how does SPI communicates? So the SPI uses MISO, MOSI, clock, and SCS. These pins are used to communicate. Now, if I explain the pin, you will have a understanding. MISO is master in slave out, means MISO will receive the data that is sent from the slave to the master. Okay, and mossy is the data that is received by the slave which is sent from the master. As the name says, master out, slave in, and this is master in, slave out. Okay, so you can read the description. Similarly, the clock is the clock signal at which the data will be read. Okay, at the clock intervals the data will be read. And then there is chip select pin. Okay, chip select pin is used to select the IC with which the master wants to communicate. So the point here is you can have one master device in the line, and this line will have multiple slaves connected to it. Okay, so the slaves S1, S2, S3. In SPI, the master has a extra pin that is CS, which we call as chip select, or you can call it as a slave select, where it will select to which slave it wants to communicate, and that slave will be responding to the master's communication. So in SPI, the master select to which slave it wants to communicate by making this CS pin go from high to low for that particular slave. So from this you understand, right, that the master doesn't need the slave address. It has the chip select pin directly connected to the slave which it can control to talk to that slave. So there is no slave id required and no master id. There is no master id, no slave id. Simply the chip select line can be used to select the slave with which the master wants to communicate. I hope you have gone through this, like MISO, MOSI, clock, and chip select. The clock is generated by master to initiate the communication. Now, how does the communication starts? So, what happens is when the master decides to communicate with a slave. So this is the slave device, and this is the master. When it wants to communicate with this slave, it makes the CS pin go from high to low for that particular slave. Then it generates the clock pulse, and then it sends the data over that clock pulse through the MOSI, where MOSI means master out, slave in. So when master is sending data, it is doing this. And when MISO, when master wants to read some data from the slave, then what it does is it will send the same clock, but it will start reading the data that it is receiving on the MISO line. Simple. So every time the clock signal decide from where the data has to be read. Now there are multiple configurations that are available in a SPI communication. It can This is a parallel configuration. See, for every slave you have a dedicated chip select line. So if you want to connect 100 slave, then the master should have 100, that 100 chip select line. So that is practically not feasible. So for small number of slaves you can dedicate the pins of the masters for particular slave as chip select, and the master can communicate with it. So what happens, the master sends the same data over the mossy or over the mossy to all the slaves, but the one to for which the chip select line is active. So for chip select to be active, it means the line should be low for that. So if the master wants to communicate with the slave 2, then it will make the slave 2 pin as low, and all other pin will be high. All other chip select pin will be high, and the only this slave will be receiving the data and responding to the masters. Okay, this is how the chip select works. So in parallel communication, I hope it is clear. The daisy chain communication. Now see here, we have three slaves, but all of them are using the same chip select line. Okay, so only one chip select line is given to all, and what and how we are configuring is that the data, that is the data the master wants to send to the slave, is first sent to the first slave, then the same data in the sent to the second, and then it is sent to the third. Now the problem here is to send the data, first data, to the like if I say that it wants to send 1 byte of data, so 1 byte means 8 bits. So each bit is sent using one clock signal, one clock. So you can just think like this: if this is the clock signal is being sent, then for every clock signal you can send only one bit. So for the first clock signal, the bit which is received by this slave will be this one, and all other will receive 0, as because in the next signal only this bit will be transmitted using this channel to this slave. So if I can, okay, I will draw and show you it will. Okay, this is also very important from the interview perspective, why in daisy chain we required more number of clocks to send the same data to the different slaves. So we can say, let's say, for suppose clock 1, first clock, we receive the first byte of data for here, and all other we are receiving null. We are receiving null. For the clock number 2, we receive here 2 byte of data. Here the first byte of data is received, so data number 1 is here, data number 1 is here, and still it is null. So for second byte, for the second clock, we receive the second clock data here, and here we receive the second here, and here we receive the first one. Why? Because the first is received here, and then via the meso line the first will be received here after the second clock pulse, and then after the third clock pulse only this will be transmitted to here, because for every clock the slave will be active. For no clock the slave, because if there is no clock the slave will not be active. So for the first clock the slave receive the first data bit, then second clock, this slave respond and transmit the same data bit that it received in from the master to the second slave. Now the second slave will on the second data on the third data bit only can transmit the data that it received from the slave one. So you see, to for the first bit to go to the last slave, that is the third slave, it takes 3 clock pulse. Similarly, for 8 bit, it will take 24 clock pulse. The calculation is simple. Okay. Now let's look into some properties of SPI. So from the interview perspective, these all things will be asked. And yeah, one more thing that I missed is that for other protocols, you have seen some specific things, like first will be the start bit, then at the end there will be a stop bit, in between some address and all. But for SPI, there is no such thing. It all depends upon how you want to send the data or how the slave is configured. In most of the cases, SPI is used for reading memory chips, that is for reading EPROMs, and for reading sensor data. So these are pre-configured IC, and they have a predefined SPI configuration. So when you want to connect to this kind of sensor, then you need to configure the master such that they can communicate. And here, the what data you want to write to the slave doesn't matter. you just follow what configuration of SPI these sensors are following. Suppose, let me just take an example. Suppose you want to write data to an EPROM, then you need to send first the start address, the, let's say, the start address of the register where you want to write, and then the data that you want to write. That's it. And while reading, you just send the clock cycle, the clocks and some dummy data, and you can read from the miso line the data that the slave can send. That's it. This is how the communication works over the SPI peripheral. Now let's look into some of the properties and understand other very important topics in SPI. First thing, it's a four wire communication. Okay, it requires four wire. What are it? That is MISO, MOSI, chip select, and clock. Chip select is always active low. Just remember it, it is always active. Active low means whenever it is low, it means that IC is active. MISO is master in slave out, MOSI is master out slave in, and clock is the clock pulse generated. So the speed it can support goes up to 10 megabits per second. It is mbps, not megabytes, it is megabits per second. Then is it a serial synchronous communication? Yes, it's a synchronous serial communication. It is synchronized using the clock, and the data is sent serially, so it's a serial communication. It's a single master multi slave configuration, so only one master and multiple slaves can be supported. The data can be sent and received at the same time, as we have dedicated lines for receive and send. We this is for receive from master point of view, and this is sent from master point of view, so we can receive and send data at the same time. Now, one of the major main question that is asked is, what is meant by this one, C pole and C phase? Okay, now you have a master that wants to talk to a slave IC. That slave IC, I told you, right? It is a pre-configured IC. So the slave IC will be supporting only some basic configurations. There it will say, okay, I will only read the data at that specific instant, and I will move the data which I have read at that specific instant of the clock pulse. What does it means? It means the data that the slave will be receiving, it will be capturing the data at a specific point in clock, because only the clock signal is where you can synchronize the data, right? So capturing the data and shifting the data in the shift register will be done at a specific instance of clock. So now, what how the clock signal looks? The clock signal looks like this. So what is specific? What are the different instance of the clock? There is a rising edge and there is a falling edge, correct? And so there is a rising edge and there is a falling edge. So for every rising edge and a falling edge, you can decide whether you want to capture the data at this instant, or you want to shift the register at this instant, or you want to capture the data at this instant or shift the register at this instant. So what is meant by shift register? I think I cleared it in the last video, but still I will repeat once more. Shift register is that, as it's a serial communication, so the data will be coming one by one, like one bit at a time. So when the first data is coming, then it has to move into the register where it will be recorded. So first data will be moved, then this register has to shift it. Now the next data should not come and overwrite the existing data, it should come go to the next vacant place. Here the second data will come, here the third data will come. So how this register will be filled? It will be filled shifting. Now actually what is there, just consider a mechanical system. Like, this is the box, anything that is coming under this box will be updated with the data coming. And and if you want to update this register, you need to pull the register in that side. Next time this portion will be inside the box, so the picture looks somewhat like this. And the data which is here in this portion is complete, and the data will now be updated in this portion. So this is how the shift register works. So now let's look into it. So just remember, we have the two things. One is positive edge and one is the falling edge. Okay, so the chip select has to be low in order to have the slave doing the communication. Then if the pole, C pole and C phase both are 0, that means at the positive edge of the clock the data will be captured. Okay, and at the falling edge of the clock at this point the shift register will be shifted. So what is happening at this point, just let's take in between somewhere here. So at this point the rising edge the data is captured. What is the data value? The data value is 1. So let me just write, show you the shift register. This is the register and this is the shift pointer. So at this point I am capturing the data, so the data for me is 1. I am updating the data here, and at the falling edge at this point I have to shift the register, so I am shifting the register here. Now here I am capturing the data, that is 0, so I am updating 0 here. Now at this instant I am shifting the register, that is at the falling edge shift the register, so I am shifting the register here. Now at the rising edge I am capturing the data which is 1, so I am putting 1 here. Similarly at the falling edge I am shifting the register, and see and at the rising edge I am capturing the data which is 1 again. So this is how the capture and shifting will work. Okay, now this combination of shifting and capture is controlled by C pole and C phase. So first thing is C pole is the polarity of the clock. So here if it is 0 and 0 means ideally the clock is low, the clock is at 0. So whenever the clock is high, then that time only the slave is active. Okay, at that time the slave is active and it will perform this capture and shift. Now let's look into the next diagram here where we are considering this one. We are considering clock is high. High is ideal, means when the clock is high the slave will not work. Okay, at this point the slave doesn't work. So what is there? And C phase is 0. So when C phase is 0 at the falling edge, so at the falling edge the data will be captured. So the data is captured at the falling edge and at the shift will happen at the rising edge. So the shifting of data will happen at here. So again we consider some middle case and look into the register how it will perform. So at the beginning it will be here. So the data is captured at the falling edge. So this is the falling edge here. So the data is 1. So data will be moved here, is captured, and then here at the rising edge the shifting will happen. So we will shift the pointer here. At the falling edge the data is captured, it is 1, so it is 1 here, and at the rising edge it will be shifted, so I shift the pointer here. Similarly at the falling edge it will be captured, so 0 here. Like this it will work. Now there is a method to remember it. Just remember, the captured will be done at the capture will be done when the slave will move from inactive to active. Okay, just remember this. So when the C pole is 0 the active state is high and the inactive state is low. Okay, so when we move from low to high, that is rising edge, so the capture will be done at the rising edge. When C pole is 1 and C phase is 0, here the active is inactive is high and active is low. So the slave will be moving from high to low, from inactive to active. So that is falling edge. So the data will be captured at the falling edge and shifting will be done in corresponding rising or falling edge. Okay, just remember this one. Now C phase just reverse the situation. C phase, if the C phase is 0, this remains the same, that always when the slave is transiting from inactive to active, capture will happen when the C phase is 0. So when C phase is 1, this is inverted. So the capture will happen when the slave is transiting from active to inactive. Same here. What is the active state? Active state is high, and what is inactive state? Low. So when it is transiting from high to low, that is from the falling edge, then only the capture will happen, and the reverse will be the positive edge where shift will happen. So I hope this somehow clears the idea. Just remember this: when 0 and 0 both are 0, that time the capture will happen at positive edge and falling edge. The capture when the C phase is 0, just remember it will always happen when the slave is transiting from inactive to active. The capture will happen when it is transiting from inactive to active. When C phase is 1, the capture will happen when the slave is transiting from active to inactive. So keeping the pole same, if we just modify the C phase, it will convert from falling edge will be capturing the data, and at the rising edge or positive edge it will be shifting the data. Okay, I hope it is clear. Now let's look into the next thing, that is what what are the basic parameters that are required to configure an SPI. So these are the basic few questions that I have put. These are mostly asked into interviews for an SPI. So first thing is whether you want to configure the device as master or slave. Second, what is the size of the data that you want to send in a shot? Like when you want to configure an SPI, it will be sending data after like a packet. So in a packet, how much data you want to send? 8 byte or 2 bytes? Then this one I just explained, C pole and C phase. This configuration depends upon the slave IC with which you want to communicate. And then this also depends upon the slave IC, whether the slave IC needs first wants to receive the MSB first or the LSB first. So when you get the data sheet of an IC, these all things will be mentioned. Now frequency is the frequency. For frequency you need to configure the prescaler. So frequency decides the speed at which you want to communicate the data. Now you have the clock pulse, right, which is used for capturing the data and moving the shift register. So you can increase the speed of this clock pulse. Let's say now you are sending clock at 8 megahertz, and the slave said it only support 4 megahertz. Then it is too fast for the slave to capture the data. That's where you will divide the 8 megahertz by 2 and send only 4 megahertz. That is the pre-scalar value will be 2 for this condition, to send the data at 4 megahertz to the slave. This all configuration will be available in the slave IC data sheet with which you want to communicate. The next thing is what all register that are required in SPI transmit and receive. Very important question that is asked. So first is the data register where data will be stored. Then there is a transmit enable flag whether the slave is ready for transmit. Then there is receive not enable flag, that is whether receive, if this flag is one, then some data is present into the data address and it is not ready to receive another data, because otherwise the existing data will be overwritten. So that is RxNE, not receive, not enable flag. So if it is one, then the receive signal is not enabled. When it is 0, then you can receive the data. Just remember data register is common, that will be used for sending and receiving. Then busy means simply the slave or the master is busy. RS is the status register, the status of the slave, whether the communication is active or the communication is low or not. And then there is an overrun flag. So these all things will be utilized in transmit and receive. So now what steps are taken for transmitting the data over SPI? So this is pretty much clear that it these steps needs to be memorized. So this is there is no such conceptual. This is the procedure in which the data will be transmitted. First the TX flag is set, it will be set, then you load the data register. At that time the TXE flag will become 0. Once the loading register is complete, then the flag becomes set again, showing that it is transmitting the data. Then you wait for the busy flag to get reset. Once the BC flag gets reset, means the transfer to the slave is complete. Okay, and then you read this DR and SR register. Reading this register makes the overrun flag as 0. So once the overrun flag is 0, it means the complete transaction is finished for our transmit. Similarly, the steps for receiving data in SPI. So the steps are: first thing, Similarly, describe the steps for receive in SPI. So in SPI, the receive is quite easy than transmit. For receive, just wait for the busy flag to become zero. Then you load some dummy data into the data register. So when you want to receive data also, you need to load the data into the data register, and then you need to wait for the RxEN flag to become 1. That is, data is not empty. Once you load the data in it, that will be transmitted via the clock. So the clock pulse will be transmitted, and the slave knows now it needs to send the data over the over the master in and slave out line. Okay, and at that time the data register will be filled, and we need to read the data from the data register to get the actual value. So this is how the SPI works. And one important thing is that in an SPI, if there is let me just write, there is miso and mosi, right? And then the clock. Let's say there is only one slave connected. So when you want to receive some data from the from the slave, so here there is a slave, so then also you need to send some dummy data, and in response the slave will be sending the data. Okay, it is not that you will, it never happens that you will keep this line as idle and you will continue to receive data. No, there will be a corresponding data sent, maybe some different thing, but still you need to send data. It can be 000 you are sending, and in response you are receiving some data like this, okay, from the slave. So here always during the receive also you need to send some dummy data in order to receive the data from the slave. So it is very important question that in the interview it is asked that how you receive data from a slave. You need to answer that we need to send some dummy data first to the slave in order to receive the data from the slave. Okay, so I hope it is clear. So if there is any question or doubt, please give a comment. I will try to reply it on the comment. Okay, thank you.